welcome to AISC's live webinar, Practical Steel Metallurgy for the Structural Steel User. Today's webinar is being presented by Doug Reese-Evans of Steel Dynamics Incorporated. My name is Brent Liu. I am with AISC's Continuing Education Group, and I will be moderating today's presentation. All right, with that, let's get started on today's presentation. I want to introduce today's speaker, Doug Reese-Evans of Steel Dynamics. Doug holds a bachelor and master's degree in metallurgical engineering from the University of Toronto. Doug has been with his current employer, Steel Dynamics Incorporated, since 1998. During his 20-year career, Doug has worked for 3 different structural long product steel mills in various capacities, including furnace metallurgist, product metallurgist, plant metallurgist, quality manager, manager of technical services and materials, and transportation manager. Doug serves on numerous industry committees, including AISC's Committee on Specifications. He serves for ARIMA, as well as ASTM International and AWS, the American Welding Society. Very pleased to have Doug Reese-Evans here today. Thanks for being here, Doug. I'm going to hand things over to you.
Thank you, Brent. Happy Steel Day, everyone. Steel metallurgy. Why, as a structural steel user, should I care about steel metallurgy? Well, although I spend my professional life working with steel, as an avid woodworker, I spend my off time working with wood. And as a woodworker, I'm aware of the differences in properties and behaviors of the various species of woods. There's some very sound reasons why maple is used for food preparation surfaces and oak is not. There's also some very sound reasons why ash is used for baseball bats and pine isn't. There are many, many other examples one could use with wood, but basically, given the situation, the choice of the correct species many times comes down to the application of basic knowledge of properties and behaviors. Similarly, for the steel user, be you an engineer, a fabricator, or a general user, you should have some basic knowledge of the properties and behaviors of steel. This is basically the foundation or the basis of our discussion this morning. The audience, I can see from the web login, is very large. I was anticipating engineers and architects, fabricators, steel users and purchasers, students and general interests. Even though the talk is about steel metallurgy, I'm not really expecting any metallurgists to be tuning in. My approach is I'm going to hit the high points. When we're talking about steel metallurgy, there is a very broad ocean of information and data available. I don't want to get bogged down in that, given the scope that I've identified. It's my goal, again, to hit the high points, kind of shave the top of the mountains and leave the deep valleys for your personal study thereafter. I'll be going through a number of slides. Our time is limited. A lot of the slides have more information than what I will talk about. I will try to highlight on the screen areas that I'm focusing on, but I have provided additional information on those slides for your self-study afterwards. And of course, I want to give a practical focus. It's no good just to give you some metallurgical trivia as it was if you don't have application to your day-to-day steel uses. When I was asked to do this presentation, the Steel Solutions Center contacted me, and after agreeing to do this talk, I asked them, what sort of things would you have me talk about? They provided me with a very long list of questions, and we kind of boiled it down to a couple of the repetitive type questions or very popular questions that they receive on a regular basis. And this will be the focus of our talk today. Essentially, iron and steel, what's the difference? Why are there multiple grades of steel? How can a mill control chemistry? And if I retest a product I get from the mill, will I get the same results as I get on a mill test report? So let's begin with the first question. What is the difference between iron and steel? Well, steels can be classified in a number of different ways. It can be classified by major alloying elements, the microstructural makeup, the method in which it's processed, or even intended applications. For today's discussion, we're going to limit the scope of steels that we talk about basically to carbon steels. Carbon steels are also known as mild steel, medium carbon steels, high carbon steels, carbon manganese steels, or high-strength low-alloy, or HLSA steels. The HLSA steels are basically a chrome manganese steel with a small concentration of microalloying elements added. So that would be the focus. Iron and steel, again, what is the difference? Well, let's look at iron. Iron is a metallic silver gray metal. It's the 26th element in the periodic table. It's the fourth most abundant element occurring in Earth. Iron is actually very reactive. So in nature, it's not normally found in a metallic state. Normally we find it in ores. They can be oxides, sulfates, carbonates, chlorates. There's some others there. Primarily the oxides are the ones that we're interested in steel and iron making. These ores can also include some impurities such as sulfur, phosphorus, manganese, silicon, and some others. Iron in its pure metallic form is actually of very little commercial use. When we use iron, we usually use it as an iron-based building material. That is, it's an alloy or a mixture of iron with some other elements. And again, these iron-based alloys can be classified by the major alloying constituent. Again, we're talking about carbon steels. We will talk about carbon steels, cast iron, wrought iron, touch briefly on pig iron or hot metal. There are some other steels out there that use elements such as nickel, chrome, moly, tungsten, etc. Those are stainless or alloy steels. Again, the scope of steels is too broad for such a short time. So again, concentrate purely on the carbon steels. Normally, when asked what is the difference between iron and steel, the short answer comes, well, iron is an element, and carbon steels are a series of iron-based alloys that have a maximum carbon content of up to 2 weight percent. And cast irons, usually I think that's where a lot of the question comes in, the difference between steels and cast irons. Cast irons are also a series of iron-based alloys with carbon, but in this case, cast irons has a carbon content of greater than 2 weight percent. If we consider iron as being wrought iron, there's a difference between steel and wrought irons. Wrought irons are actually obsolete, but they can be considered the precursor of modern low carbon or low mild steels. Pig iron is also thrown around a lot in the industry, mostly on the steelmaking side. So if one considers iron as a pig iron, there is a difference. Pig iron is really the product of a blast furnace in the solid form. In the liquid form, it's known as a hot metal, and it typically has a very high carbon content between 3.5% to 4.5%. It has absolutely no structural uses. It's really a feedstock for steel making. So if we look at the range of iron-carbon alloys that we're going to consider, you can see that there's this definite distinction or separation at the 2 weight percent carbon level. Our carbon structural steels all lie down in this range. There are some higher carbon content steels that have particular applications, but you typically don't run into them in a structural application. So again, the question is, why this 2% weight difference? Well, the answer actually comes down to something known as a phase diagram. So we're going to jump a little bit into metallurgy here. What is a phase diagram? Essentially, a phase diagram is a graphical representation showing temperature versus composition for an alloy. In this case, it's a 2-component alloy. I've given the hypothetical chocolate vanilla phase diagram. We can see on the vertical axis we have temperature. On the horizontal axis we have weight percent chocolate. So as we increase the amount of chocolate in the vanilla mix, we end up with different phases. These different phases are delineated by solid lines. So in this region here we have a solid vanilla. In another region here bounded by these solid lines we have hot chocolate as a liquid. In another region we actually have vanilla malt with solid chocolate chips. On a phase diagram, if we change either temperature or we change composition and we cross a line, for instance here, if we change temperature from temperature 1 to temperature 2, we see at point 2 we hit the phase diagram boundary line. So what happens is we start to have solidification of solid chocolate out of the hot chocolate where we still have a liquid. So we have a 2-phase mix here. As we continue to cool, what happens is that liquid solidifies and we end up with a duplex solid. So really what you have to understand from phase diagrams, again, it's a temperature composition-based diagram. The lines delineate changes in state, be it from liquid to solid, or in some instances, as we'll talk about in steel, it actually delineates changes from solid to another solid. In this phase diagram, there are equilibrium, which means slow change, and the reactions shown in the diagram are 100% reversible. So upon heating, we can go from chocolate ripple to vanilla malt to hot chocolate, and again, as we solidify, it'll go backwards. Applying this to iron and carbon, the phase diagram is shown here, and the 2% carbon separation between cast irons and steels really has to do with this phase here known as austenite. Austenite is a homogeneous or a single phase in which all the carbon is in solution in an iron matrix. Once we get above 2%, we run into what's known as a duplex phase, where we have austenite plus we have iron carbide or cementite, or in the case of cast irons, we have a phase known as graphite. So really the long answer as to what's the difference between iron and steel is that the properties of an iron-carbon alloy are controlled by the microstructures of the material, which are in turn controlled by the chemistry and the processing of the material. So we're going to explore a little bit about that right now. One of the very unique properties of iron-based alloys, or iron itself, is that iron is an allotropic solid. Allotropic meaning it has different crystal structures at different temperatures. Again, we need to delve a little bit into metallurgical theory here to understand what that is. So if we look at the basic nature of metals, metals are crystalline solids, which means they have their atoms arranged in a repeating 3D pattern. Out of that pattern, we can take a small segment that represents the smallest symmetric repeating segment in that lattice. That's known as a unit cell. There are 14 different types of unit cells that metals can form. The three most common are body-centered cubic, face-centered cubic, and hexagonal close pack. Those are the metals that are most commonly used industrially. Body-centered cubic refers to the unit cell having this cubic structure in 3 dimensions, plus an additional atom in the center of the body. Face-centered cubic means, again, we have this cube, atoms at each apex of the cube, but we also have atoms centered in each face of that cube. These are the 2 structures that we're primarily going to talk about. The other thing we need to know about metals is metals are made up of grains. And what grains are is if we take that crystal lattice and we have a particular orientation, we will find that where another orientation intersects, we have a mismatch, like along this line here, where you can see that these atoms across the boundary, excuse me for a second, these atoms across the boundary are not lining up as they would do regularly if this was a uniform crystal lattice. So this intersection is a grain boundary. If we were to pair a metal sample and look at it under a microscope, we would see something very similar to this, where the dark lines are the grain boundaries. What this really represents is you have the grain boundaries, and again you have some random orientation of the crystal axes within the neighbors. Going back and looking at iron, we said it was allotropic, so it has different packing at different temperatures. If we solidify pure iron from a liquid, it will solidify to a body-centered cubic, which is known as delta iron. As we cool that further, we get into a region here where the atoms rearrange themselves. It's already a solid, but they have a better packing efficiency and a lower energy at this temperature range to repack themselves in a face-centered cubic phase. This is known as austenite or gamma iron. And again, as we cool even further, they will rearrange themselves again, go through a solid state phase transformation, and realign themselves back into a body-centered cubic state, and that's known as alpha iron or ferrite. Now, we did say that steel is made up, or carbon steels are made up of an iron base with carbon. Where's carbon in this picture? The carbon atom is actually half the atomic radius of iron. So in that matrix, what happens is it occupies what's known as an interstitial space, basically in between the atoms. So here we are, 2D, you can see where the carbon atoms lie, and 3D, possible locations for a carbon atom. Why is that important? Well, in this change from the face-centered cubic or the austenitic state to the body-centered cubic ferritic state at lower temperatures, we run into some difficulties. If we look at the unit cell, we can see that austenite has a larger cube than does ferrite. As a result, when they transform, and due to atomic packing, we find we have a difference in carbon solubility. So austenite can retain up to 2% carbon, whereas ferrite can only retain up to 0.02% carbon. So upon cooling, we have this problem. What happens to the additional carbon? Graphically, I'm showing here an austenitic grain with ferrite or alpha iron going through a phase transformation, growing into the austenite, so this would be cooling. Again, we have this 0.2% carbon solubility versus 2% carbon solubility. So what happens as this front grows, as the crystals realign themselves, the carbon gets rejected out of the ferrite, and it must go somewhere. So it diffuses over and forms a new carbon-rich phase. The morphology or the state of that phase, its volume, its spacing, is all dependent upon the amount of carbon you have in the alloy, plus interferences of other alloying elements, and the cooling rate. And as we talked about phase diagram, upon heating, this is reversible. That carbon goes back into solution, back into the austenite, up to 2%. This change forms the basis of all the heat treatments of iron and carbon alloys. What this actually looks like metallographically is we end up with a duplex microstructure, two phases in the microstructure. The dark lines here represents the carbon-rich region, which is known as either iron carbide or cementite. It can take up to 6 2/3% carbon, which it makes it very strong, very hard, very wear resistant, but it also makes it extremely brittle and unweldable. Whereas the white parts in the microstructure are made up of ferrite with the lower carbon content. It's much weaker than the cementite. It's also softer, more ductile, and weldable. So we get this thing, the combination of the two together is known as perlite. It's not really a grain, it's a colony, but very often, for the sake of simplicity, we'll talk about perlite grains. If we were to look at different steels with different carbon contents under the microscope, we're going to see different amounts of ferrite and perlite occurring. So if we go below 0.02% carbon, we're going to have a fully ferritic structure. As we increase the carbon, you're going to start to see some random colonies of perlite. As the carbon increases, the volume of the perlite also increases until we get to around 0.8% carbon, in which case we get to what's known as a eutectic or a fully perlitic structure, in which all the grains or colonies are actually perlitic. Above that, what happens, if you compare these two slides here, 0.8 versus greater than 1% carbon, we actually see the dark grain boundaries disappear because we have the additional ferrite now precipitating out at the grain boundaries, and as a result, we can actually start losing some strength. Now, I did say that for this change to take place to form the perlite, we do have to have some diffusion occurring. One of the problems with metallurgy is we tend to get a bit jargony, so I'll try to define terms as we go along. Diffusion is a temperature and time-based reaction. If we have this transformation going on slow or in equilibrium, we get the perlite formed. If we don't, we end up with non-equilibrium steel phases. Some you may be familiar with, upper and lower bainite and martensite. Graphically, why we get these non-equilibrium phases, if you look at this picture of traffic and you consider the motorcyclists as being carbon atoms and the cars and buses as being iron atoms, If we're moving along in steady state, the traffic's moving, then the motorcyclists or the carbon can move in around the cars very easily. But if we don't give enough time or temperature, i.e. the traffic comes to a halt, what happens is the carbon gets locked into a place it doesn't want to be. Those are these non-equilibrium phases. Now, bainite has some undesirable properties. With low carbon bainite, we can actually get some desirable properties, such as low temperature toughness for steel, improved strength, very good weldability. Martensite, on the other hand, is something we don't want. That comes from very rapid cooling or quenching. We end up with a very hard, strong, wear-resistant structure, but it also has extremely low ductility and consequently low fracture toughness, so that's not desirable. Now, metallurgists have characterized the time-temperature dependency on the austenite to ferrite phase transformation. They've come up with things known as TTT diagrams. There's a variation on that called a CTT diagram. But basically it lets us predict, based upon temperature and cooling rate, what sort of microstructure we'll end up with. The curves do change based upon alloying. For instance, here in the second curve, we see we have a 4% carbon, or sorry, 0.4% carbon steel. If we increase to 0.2% manganese, you can see that there's actually a change in the shape and position of the curves, time-wise and temperature-wise. Again, this is predictable. Again, it forms the basis of heat treatment. It's important in welding. It's important in processing. So that's the microstructures of steels. Well, again, the question was, what's the difference between iron and steel? And reading into the question, I think a lot of people may come from the standpoint, what's the difference between steel and cast iron? Well, as we go through this phase transformation from cooling from austenite down to what would be a ferrite state, actually in cast irons what happens is we have enough carbon. We don't form ferrite. We form a pearlitic structure as we've done before in the steels. There's pearlite grains. But the problem we run into is this additional carbon, or the excess carbon, will either form a 3D network of graphite flakes, or, given the right alloying elements, will form graphite nodules instead of the flakes. The problems with the graphite within the material is that graphite is a very soft, low-strength material. Essentially, the lead in your pencil is graphite. So it acts like a void in the structure. So these graphite flakes act as stress risers within the cast iron. It gives us very low strength, low ductility, and very low notch toughness. The benefits of cast iron, if you're doing some machinery bases or you're doing some ornamental work, very machinable, good compressive strength, and excellent castability. From a structural standpoint, there have been historic uses of cast iron in static and compressive states. Here's an example of some 19th century iron facades that are still performing well today. Cast irons has also had a history of use in bridges. One of the first metallic bridges was the Iron Bridge in Coalbrookdale, UK. It opened in 1781. Still stands today. It's actually a UNESCO World Heritage Site. This bridge formed the basis for use of cast irons and bridges for the next half a century. This bridge's success probably relies upon the fact that it was built using carpentry principles. Basically what they did is they mirrored what they had been doing in wood using cast iron. Unfortunately, cast iron, as we talked about, has some undesirable properties from a structural engineering standpoint. Again, those are low notch toughness, low strength, low ductility, and stress risers due to the graphite flakes. Between the 1830s to the 1890s, there were a fair number of cast iron bridges, mostly put into railroad services. There were a lot of incidents. The photograph here clearly shows a locomotive under the bridge, obviously not a good situation, and we see places where the cast iron beams have clearly fractured. Again, due to the nature of cast iron, they're not suitable for this type of application. Now, there is a class of steels out there known as cast steels, and basically they are just steels cast into a particular shape. Don't let the word cast throw you, because cast steels are not the same as cast irons. Again, cast irons have this microstructure that's not desirable from a structural standpoint, being the graphitic flakes or being the graphite nodules. Cast steels can have any of the chemistries that regular steels, carbon steels do. They can be cast of any of those chemistries. They will tend to have a ferrite perlite type microstructures. There can be variations based upon processing. We do need to be aware of some differences in the structure. You don't get the nice uniform equiax grains I showed you before. There is a variability in the cast structure just due to the nature of casting. But again, cast steels can be engineered for suitable application in structural uses. So again, don't let the word cast worry you. The difference comes between is it a steel or is it truly a cast iron. Also did mention some alloy out there known as a wrought iron. Very often we think of wrought irons in ornamental work. Actually, wrought iron could be considered the precursor of modern low-carbon steels. Steels, if you really stop to think about it, come from a steel-making or liquid process, such as Bessemer, open hearth, basic auction furnace, or electric arc furnace. Whereas wrought iron is really the product from the puddling furnace. Basically, it was never fully liquid. It was a pasty thing. It goes through a series of processing from rolling, slitting, stacking, reheating, reforging. So it's really a wrought or a hammered structure. The chemistry, very similar again to low carbon, mild carbon steels, less than 0.25% carbon. The literature of the time that wrought iron steels were being used reported between 0.05 to 0.15 weight percent carbon is the usual chemical constituency. The chemical properties were fairly decent, albeit low for today's uses, around a 23,000 yield strength, 46,000 tensile strength. The problem with wrought irons, though, due to the processing, they have a very high volume fraction of oriented slag or oxide inclusions. So if we look at a microstructure of a ferrite, perlite, low-carbon steel, seen that before, versus wrought iron, what we do see is these very, very large inclusions in there, and that affects the microstructure. Now, wrought iron has had a history of structural application. For instance, the Eiffel Tower is built out of wrought iron, but one of the problems with wrought or puddled iron is because of the nature of the forging of it, it is prone to delamination, whereas steels properly processed are not. So the long answer was the difference between iron and steel. Comes down to iron as an element. If we refer to cast irons as irons, there is a big difference in the microstructure and in the carbon contents. And again, keep in mind, cast steels are not the same as cast irons. If we're referring to iron as a wrought iron, very similar to a steel, but because of the large slag volume, we have some limited applications it can be used for. If we refer to iron as pig iron, again, that's a steel-making material. So, in a nutshell, that's, again, at a high level, what the difference is between iron and steel. Why are there multiple grades of steel was the next question I was asked. Isn't steel just steel? Well, let's first look at what a grade is. Webster's defines a grade as either to arrange in a scale or a series, a position in scale or rank of qualities, a standard of quality. Some common structural grades, A572 grades 42, 50, 60, 65, etc. There's A588 grades A, B, C, and K. There's A36, A992. These different structural grades loosely meet Webster's definition in different manners. Our industry tends to look at a grade a little bit different than others. Grade basically gives us a classification or systematic arrangement based upon certain characteristics, such as composition, be it alloying elements, manufacturing process, whether it's hot rolled, cold rolled, casting method, rimmed, capped, semi-killed, what have you, or even the product form, be it a bar product, be it a structural product, tubing, a shape, etc. In non-ferrous industry, they're a little bit more regular in their definitions. They classify a grade denoting chemical composition, a type denoting deoxidation, and a class denoting some other attributes such as in strength. Again, in the steel industry, we kind of muddle those up and use them interchangeably. For instance, an ASTM A572 grade 50, the 50 defines or describes the strength level, but typically we'll call that a grade 50, or we'll use the A572 grade 50 as the grade. So really, from a steel standpoint, the specification details the chemical and mechanical properties or requirements and restrictions. Why multiple grades, though? Well, there are different specification bodies who issue grades, such as AASHTO, ASTM, ABS, etc. The difference between them really comes down to what their focus is. AASHTO is bridge and highway. ABS tends to be shipbuilding. ASTM can be for general, or there can be some specific uses based upon the grade. These different bodies, as they issue the grades, they can adopt and adapt different grades. For instance, if we look at AASHTO M270, compare that to ASTM A709 and ASTM A57250, we will, if you go into the specification, you'll find that basically ASTM issues the A57250. It's a 50 KSI yield strength material. It's for use in bolted, riveted, general structural applications. Now, AASHTO's taken this grade 50 material and they've incorporated it into their M270 specification. AASHTO, being a metric spec, changes the 50 KSI to 345 megapascals. So what we end up with is essentially the same grade, different name. Now, by agreement, AASHTO republishes the M270 in ASTM as a specification A709. So what we have is a case that A70950 is essentially the AASHTO M270 345, and it's the same as the A572 grade 50. Now, there may be from time to time some slight differences due to committee activity and publishing cycles, but in essence, it's the same grade with different names. We can also look at the grades for very specific product applications. For instance, if we look at the A709, you can modify that grade by adding a suffix T123 or F123. So the A70950 is the base grade, but due to very specific applications, be it a non-fracture critical application or a fracture critical application, we've modified the grade. So what happens is we take the base requirements for A70950, which again is A572 grade 50, and we add some Sharpie requirements. For non-fracture critical, we require a minimum impact energy of 15 foot-pounds. For fracture critical, a minimum impact energy of 25 foot-pounds. And then depending upon where this is going to see application, we have a service temperature zone. We will change the testing temperature. So if we, for instance, specify an A70950 T1, it really is a base grade of A70950 plus the T1 Sharpie requirements for a very specific application, that being non-fracture critical for use at 0 degrees Fahrenheit or greater. We can have a A70950 F3, again, very specific requirements. You take the base grade of A70950, you add to it specific Sharpie requirements of 25 foot-pounds for use in a fracture critical application, typically between minus 30 to minus 60 Fahrenheit. We can also have multiple grades because there's been some additions or restrictions added to some grades. For instance, if we compare A572 grade 50 versus ASTM A992, what we'll see is grade 50 or 572 was originally published in 1966. At that time, there was very limited electric arc furnace steel production. It was mostly integrated. Therefore, we had low residuals. Cost money to add them. In 1998, when 992 was published, there was no domestic integrated steel production of shapes. It was 100% electric arc furnace. There was a fairly high, or not high, but moderate level of residuals in the scrap. So A57250, the base grade was redefined or had restrictions added to it to cap the residual level. We added a maximum yield strength, a maximum yield to tensile ratio, some carbon equivalencies, etc. So again, we can have different products. I was going through the cupboards in my kitchen the other day, and I came upon a box of all-purpose baking mix. On the back were some recipes. Highlighted the ones for pancakes and waffles. If you look at the recipe as I've highlighted there, you'll see that they have the same chemistry. You'll see that predominantly they have the same processing, but we end up with a different product. So if we were to turn that into steel, we may or may not actually write a different specification based upon the product and that product's application. And then to further complicate things, we have an industry practice called multi-certification. If we look at a hypothetical W16 by 36, and here's the chemical analysis reported on the mill test reports, and the physical properties also reported on the mill test report, we can compare those to the different grades. For instance, A36. A36 also was published back in 1966. It's still in use today, although as steelmakers we prefer to dissuade its use. Things tend to be more of the 992. But if we compare our hypothetical W16 by 36 and the MTR analysis versus the requirements for A36, we see that it does meet the limited chemical requirements. We see that it does meet the physical property requirements, including meeting the range for tensile strength. So does that 16 at 36 meet A36? Yes, it does. For A572 grade 50, again, if we check the chemistry, we see that it's all under the maximum. We see where there's a range. Our analysis meets that. And our physicals are above the minimum requirements. So we can also call that particular products also A36 and A57250. We talked before, noting that A70950 is essentially the same as A57250. Again, checking the requirements, we see that it meets that grade. And if we go to 992, which this shape probably was intended to be made as originally, we find it meets that requirements. So in fact, that shape actually meets all 4 grade requirements and can be certified as all 4 grade requirements. That does cause some concern and consternation for some users. Really, the analogy I like to use to make it clear, if we look at this handsome fellow on your screen, his first name is Doug, his last name is Reese Evans, and in grade school they called him Reese. So you can call me Doug, you can call me Douglas, you can call me Mr. Reese Evans, or you can call me Reese. Whatever you call me doesn't change who I am. But whatever name or title you use is based upon a context. It's the same with our steel grades. The analysis doesn't change what it is. That is what it is. The grade is what context is it intended to be used in. So if I multi-cert something, it can be used in an application someone's designed for A36, yes. If I certify it as A709 and I certify it as 992, then yes, it can be used in highway work because it meets those requirements, or it can be used in general structural applications. So the answer to the question, why multiple grades, is different specification bodies, different products or product applications, cross-adaptation or adoption, same materials with different grade names or multi-certification. And again, I know this is a little bit confusing to some people. Again, look at the context. What name do you want to use is based upon the context.
Excuse me, Doug.
Yes.
Before we move on, can we address a couple questions?
Absolutely.
One question here is why can't I get single angles in A992?
That would go, you'd have to talk to the particular manufacturers or group of manufacturers who make the angle. 992 was originally intended to be used in structural wide flange shapes. That's where its origin was. Over time, the committee has expanded that to general application. There are some processing things which we'll see here a little bit later on that things like angles may be too light, that you're getting too much strength in them, that you can't get the alloys or the carbon levels down low enough that actually meet the 992.
Okay. And then one other question. This is in regards to temperature application. I assume high temperature, but where can I get the yield strength of steels such as A992 or A572 versus temperature, specifically looking at rupture stress versus temperature?
I don't have a reference at hand. I can tell you, I would probably point the questioner back to the Steel Solutions Center. AISC does have a committee or task groups working on fire engineering, and that is some of the stuff that they are looking at. So that committee probably would have that data or references to that data at their fingertips.
Okay. Thanks, Doug.
Okay. All right. Third question that was posed to me is, how can a mill control chemistry? Isn't it just really based upon what scrap is used? Well, let's look at the steelmaking process. The chemistry control comes in the liquid. So we start with raw materials. We may or may not go through iron making, and we have steel making. Once we get over here to casting, the chemistry is essentially set. You're done with it. So let's quickly just look at iron making. Sorry for the delay. Iron making is done in the blast furnace. Basically, we put iron ore, coke, and limestone into the blast furnace in the top, and as it descends through the blast furnace, we have oxidation of the coke going to carbon monoxide gas, and it reacts with the iron oxide, reducing the oxide from high states of oxidation all the way down to liquid iron. We also do get some secondary reactions where we have reduction of silicate, so you get some silicon content in the hot metal. Also, any reduction of manganese oxides that came in with the ore, you have reduction of manganese. Carbon also gets picked up into the iron basically through dissolution. So what you end up with is an output of hot metal in the liquid that goes directly to steel making, or you get pig iron, which is in the solid state. Again, high carbon, 3.5 to 4.5% carbon. No structural applications. It's really a feedstock for steel making. If we stop and look at what the steel and iron making process is, as they taught us in school, it's really a reversal between reduction and oxidation reactions, where we start with the ore, very high an oxygen content, typically 30% oxygen, and through iron making, we reduce or remove that oxygen till we end up with a hot metal, very low oxygen, but very high carbon, typically too high, again, 3.5 to 5%, too high to be used. So in steel making, we go through some reoxidation procedures where we reduce the carbon. We also reduce some other desirable elements such as manganese, silicon, and aluminum till we get to a desired tap carbon. And then after that, we've introduced oxygen back into steel. We have to go through some deoxidation. There are some alternates to the blast furnace, things known as direct reduced iron, hot briquetted iron, sponge iron. They are very desirable from the steelmaker standpoint because they have shorter furnace campaigns. Blast furnace campaigns can last on the order of 7 to 15 years, depending upon the way it's operated. Alternate iron can be operated on a on-off manner, and you get similar chemistries as to you would in the hot metal or the pig iron. Some example processes are given. Nucor's got the iron carbide down in Trinidad. They're currently building a plant in Louisiana. My company, Steel Dynamics, we have Iron Dynamics operating at our flat roll division. They produce a DRI, but they also melt it in a furnace to give us hot metal. And also SDI is involved in the Iron Wasabi Iron Nuggets project, which gives you a solid DRI product. So those can be some of the raw materials going in. Now, I'm going to talk a little bit about steel making. I'm going to go back, give you a little bit of history. I did talk about wrought iron and puddling. I just thought it might be interesting to see where the differences in wrought irons and steel come from. Basically, in the puddling process, they put pig iron into the hearth. It is heated in a reverberatory manner. So we burn some sort of carbonaceous fuel over here, but we don't get any carbon pickup. What happens is through a furnace door, a steel or puddler will reach in with a bar and he will stir this liquid mass of pig iron and expose the surface to the furnace environment, at which point the dissolved carbon reacts with the oxygen in the environment. So metallurgically what is going on is we have a liquid here, pig iron melts at a very low melting point. We start oxidizing, increasing the carbon at a particular temperature, and after a while we start to raise the temperature. We will reach a point where we never get fully liquid once we start doing the puddling process. We actually have a pasty ball. When it comes of nature, it actually starts to solidify going here into the austenitic region. At that point, it's pulled out of the furnace, and it's rolled and it's hammered. Those pieces are sheared, stacked, reheated, and they're re-rolled. And they were rolled in something known as merchant bar. And there's a term that actually hangs over to today. Again, low carbon, extreme variability in the carbon content between batches. The puddling process was essentially supplanted by the Bessemer process. If everyone listening isn't familiar with the Bessemer process, they've at least heard the name. It is really the first tonnage steel making that came about. What happened is they took hot metal from the blast furnace, put it into a converter, blew air through the bottom. The oxygen in the air reacted with the steel, primarily the silicon and the manganese first, then with the carbon that's dissolved within that iron, and it raised the temperature. The advantages of this over the puddling process was the speed. Bessemer, you could get 20 tons in half an hour versus 3/4 of a ton in 4 to 6 hours out of puddling. The Bessemer process is autogenous, which means you didn't have to add any additional heat or energy. One of the biggest advantages over puddling came in the cost. The Bessemer process was first commercially used in the United States in 1856. If we look at the cost of Bessemer steel versus puddling iron at that time and convert it into today's dollars, we would find in 1856 puddle iron cost over $5,000 a ton, whereas Bessemer steel cost $800 a ton. But there were some processes with the Bessemer process, and that was primarily you could not remove sulfur or phosphorus. That's because there was no slag. Also, the process was so rapid that you could not do real-time chemical analysis on your batch. The techniques at the time just weren't fast enough, and you can't use scrap. If we were to add scrap to the hot metal, you'd basically end up with a solidified mass. From the structural arena, those who have been around for a while or have read some older specifications will often come across a warning against acid Bessemer steel. So I thought at this point we'd just make mention of what the difference is between acid and basic steel making. Really it comes down to the type of refractory and slags that are used. It wasn't until 1879 that a gentleman named Thomas discovered that sulfur and phosphorus could be removed from liquid steel by the use of a basic slag. An acid slag is basically a silicate-based refractory slag, and a basic slag is a dolomitic or a lime-based. So when you hear something acid Bessemer or acid practice, it refers to the use of acid refractories or silicate-based refractories versus a basic practice, which uses basic refractories. The acid Bessemer was very common in the United States due to the fact that we had lower phosphorus ores than they did in Europe. and the cost of acid refractories were a lot cheaper than the basic ones at the time. Okay, so I mentioned two other terms, and I promised not to be too jargony. What's the difference between a refractory and a slag? Essentially, a refractory is a material of very high melting point that's suitable for the use in lining of a vessel. Here's a picture in one of our ladles here at Steel Dynamics. The refractory back here is basically a brick. It's a lining. It goes inside a steel vessel. Without that refractory lining, if we put liquid steel into our ladle, which itself is made out of steel, would be analogous to putting a cup of hot coffee into a mug made out of ice. It's not going to be a good situation. So the refractory basically contains the liquid steel. Slag is made up of a similar base as is the refractory, be it dolomitic, be it lime-based, be it silica-based, but slags are liquid at steel-making temperatures. They're lower density than steel, so they float up on top. Again, you can see here the orange regions are molten steel floating on top. The white spot here is a little bit of where a bubble of steel is burst forth. The slag acts as a blanket, a thermal blanket to help us maintain the temperature. It prevents reoxidation of the steel encountering the furnace environment. It also acts as a reservoir to absorb and retain impurities, either oxides or sulfides, which is very useful for our refining processes. There is a chemical equilibrium between steel and slag. I was taught in metallurgy school that you really don't make steel, you make slag. The analogy there would be a flywheel. The slag has the chemical mass. You must act upon the slag, because if you don't, it's going to pump things back into the steel. Slag is a byproduct of the steelmaking process. It is a sustainable material. It does get reprocessed. Slag typically gets crushed and classified and can be used as aggregate for concrete, can be used as road-based, railroad ballast, etc. Okay, other steelmaking processes. At the same time, around the same period as Bessemer came out, a competing process known as the Siemens or the open hearth process was developed. This used scrap and pig iron initially, got charged to the furnace. Again, a reverberatory furnace, so heat was impinged upon the solid to melt it. After a period of time, hot metal was added. Very slow process. The advantages were heat sizes between 50 to 300 tons. Slow, you could sample it, get the chemistry. You had fairly good control over sulfur and phosphorus, again, depending upon what furnace linings and refractories you did. Had an advantage, again, we could use a solid. If you had surplus hot metal capacity, you could solidify that and use it at a later date. You could use scrap. Some of the difficulties, though, it was a long process, and it was reliant upon a source of hot metal. The open heart furnace process basically was obsoleted in the United States in around 1967. Worldwide, the last open hearth stopped operating in China around 2001. What supplanted the open hearth was the basic auction furnace, very similar to the Bessemer process, where we put hot metal into a vessel, but in this case we can also use solids. We can use that pig iron, we can use scrap, we can use alternate iron. We add hot metal. The process basically is we're burning out those elements again that generates chemical-based heat. So oxygen is blown in at supersonic velocities. The advantage is it's autogenous. Again, we don't have to add any additional energy. And even though scrap is used, it's typically only used around 25% of the burden. So we do get dilution of residual elements. Difficulties with this is you must be connected to a hot metal supply. And then again, the final steelmaking process out there is the electric arc furnace. It does use a number of different inputs, primarily scrap. Although steelmakers, we do use pig iron and alternate iron. Interesting to note, the first electric arc furnace operating in the United States was by U.S. Steel at Southworks in 1909, and they used 100% hot metal charge at the time. Last 10 years, Steel Dynamics flat roll division, coupled with their iron dynamics division, has been using hot metal charges to supplement and for dilution purposes. process of the electric arc furnace is you charge, you melt, you tap, and then you refine. Advantages is very flexible. We have, as I've just gone through, a variety of input sources. Can be shut down very quickly, turned on very quickly. Problem we have is it's non-autogenous. We have to add additional energy, be electrical and chemical. And because we have a higher scrap content, we do have to be cognizant of residual element control. So overall, looking at the metallics input to steel making, we see that other than Bessemer, which has been obsolete for most of our lives, all other steel making does use scrap as the metal source. So the question is, how do we control chemistry? Usually is centered around scrap. Well, scrap isn't something that we just throw into the furnace. Steel makers, we purchase scrap from scrap producers, scrap yards. They actually grade and classify the scrap into sizes, past history, expected chemistries. As steel makers, we blend those, taking into account cost, density, melting efficiency, and chemistry. So the question is, how can we control the chemistry? Well, scrap has had a long history of steel making, and really it comes down to the careful selection and blending of scrap and dilution. But chemistry is not the only aspect to making steel. If we really considered what goes into making the mechanical properties, we'll find that mechanical properties such as yield, tensile, elongation, etc. are a function of both chemistry and microstructure. So we also have to control other parts. We'll get to microstructure here in a moment. The chemistry is more than just the scrap, though. As I said before, during steel making, we have a loss of elements, carbon, manganese, silicon, etc. So we have to go through some additional processes where we build that back. There's a series of elements or classification of elements, such as oxidizable elements. Those all get removed. We have to add them back. There are elements such as sulfur, which we can remove. One of the few elements we can actually remove. Other elements come either in from the ore or from the scrap. And again, we control those through careful blending and dilution. In secondary steel making, we basically go back and we add back in those elements. We also control temperature. We make sure the steel is homogeneous from a temperature and a chemistry standpoint. And there may be some additional processes based upon the type of steel being made, be it degassing. So let's quickly look at some strengthening mechanisms. Why is chemistry really important? I'm going to look here again. We're going to go back and do a little bit of metallurgy. If you remember our crystal matrix, we have a regular repeating lattice of atoms. They can have defects. There's 4 common defects. We're going to talk first here about what's known as an edge dislocation. Basically, a dislocation is an extra plane within that structure. What it does is it creates a stress around the edge or the end of that dislocation. When we apply a stress to this, what can happen is the bonds around this edge dislocation can break from one another and slide through the lattice. So if we look at a pre-stress condition here, the red atoms, the bonds get broken and the bonds actually move through the structure, whereas the atoms themselves stay where they are. The net effect is we have this dislocation plane moving through the crystal. We have a permanent shape change, but we can do that at a much lower energy than it would require to actually shear an entire plane of atoms or move this atom over to this location. Going back to our unit cell, if we stop to really analyze that, what we would see is that different orientations or packing efficiencies have different strengths. Here in the body center cubic, here's 2 different orientations. Along the face, very weak, easy to cause slip. Through the body, stronger, very difficult. So on the granular level, steel is anisotropic, which means it has different strengths and different directions. At the macro level, the random orientation of grains actually acts on an average behavior, and that's the properties we measure. Going back to our crystal lattice, other imperfections we have there, we have something called interstitial. We talked about carbons fitting between the atoms. We also have substitutional elements. Those are alloying elements that can occupy the lattice place over an iron. What they do is they, again, create stress in the lattice, and they can pin these dislocations from moving. And when they pin them, they increase the strength. Different elements can have different effects based upon the amount of element added as to how much they can affect the strength. Okay, in the sake of time, we're going to skip over a minor one here. I want to look at what the mechanical properties are. Going back again to an earlier discussion, we talked about grain boundaries as being intersections between the lattices. They're a mismatch in that structure, so they create strain. There's unsatisfied bonds there. In nature, things tend to want to go to the lowest energy state. So given the fixed volume, if I have small grains, I'm going to have more grain boundaries. Grain boundaries being higher energy, I'm going to have higher energy. So overall, given the right temperature and time, we have the impetus for the grains to grow by consuming smaller grains to lower the overall energy. Now, the important thing to recognize is dislocations and vacancies do not cross grain boundaries, but they pile up there. So essentially what I get is if I have a finer grain size, I end up with a stronger steel. Well, how do I get a fine grain size? Grain size really comes through the rolling process. Rolling, basically, we take a shape, pass it through counter-rotating rolls. We take a initial cross-sectional area. Due to conservation of matter, the overall cross-sectional area does not change, but we do get elongation. There's a myriad varieties of rolls, shapes, and configurations that can be used based upon product to get what you want. Essentially, though, for all hot rolling, the same thing is happening. We start with a very large grain size going into the rolls. They get plastically worked or deformed. That adds energy. We have enough temperature for in the austenitic range that we'll start to have recrystallization. I won't go into the mechanisms that cause that, but we end up with a finer recrystallized grain size. And of course, if we let it stay at temperature, over time, they'll start to grow. The net effect is the more reduction I have, the finer grain size that I will have. So we see here a very small shape with a very high reduction ratio. We get very small grains. Again, given time, they will recrystallize and have grain growth. In a larger or thicker shape, I may only have reduction or elongation at the surface, and I may have grains in the center that are unaffected. So going across the cross-section, I can have very fine grains at the surface, coarser grains in the center. Again, I won't go into what causes recrystallization other than to state a fine austenitic grain size will lead to a finer grain size. So let's just look at a practical application here. If we again take a hypothetical size of 16 at 36 and compare that to a hypothetical 14 at 398, obviously we have a difference in flange thickness. We've just discussed what that's going to do to the grain size. Carbon's about the same. The 14 at 398 actually has more chemistry, more manganese, more vanadium. If chemistry gives it strength, you would think you have a stronger shape with the heavier size, but in effect, you look at the yield and tensile, we are going to have less strength with the heavier size. Why? Because we have a greater rolling reduction, lower rolling reduction with the 398, so we end up with a coarser grain size versus the 16 at 336. So kind of counterintuitive. So what we're seeing is grain size in this instance has contributed more to strength than has chemistry. There are some other things that steel producers can do to affect grain size. Typically a hot rolled is air cooled. We can control the mill pace, section size. Some instances we can apply selective cooling to take that heat out, to remove the temperature time factor to it. There's a grade known as A992 that actually uses a quench self-temper process. So we end up with a different microstructure. We also have another strengthening mechanism known as precipitation. When we add things like microalloys, if you remember back, we talked about high strength, low alloy. The steel being a carbon manganese steel that's modified by adding a particular alloying element. What they do is they form very fine particles or second phases, kind of like we talked about with the cementite within the structure. These be nitrides or carbides. What they do is they act as nucleation sites. They give you finer grain size. They also act as a macro block to dislocation motion. So practically, what do these strengthening mechanisms do? How does that give us mechanical response? If you're familiar with the stress-strain diagram, you'll know initially as we load a steel, we have an elastic response. What essentially happens is we take a lattice at rest, we stress it more. When we remove the stress, it behaves 100% elastically, goes back to the original shape. Really what has happened here is the interatomic binding forces govern. We haven't had any plastic deformation. Okay? In carbon steels, we're not sensitive to structure. It's unaffected by grain size and, for the most part, alloy content. So from a standpoint where yielding is a design consideration, even though on the granular level, steel is anisotropic, at a yield level, it is isotropic, means it has the same properties in any direction, and it is temperature dependent. Ultimately, when we add sufficient stress, what happens is these dislocations we talked about become unpinned, and they start to move. In very low alloying concentrations, we actually get a sharp upper yield point. It's kind of an activation energy where those dislocations have resisted that slip, or sorry, the interstitial atoms have resisted that slip. They finally let go, and we get a dramatic decrease in the amount of stress that is required for yielding. This is called the Luder's plateau. And again, because the steel is made up of randomly oriented grains, we don't actually get a straight line behavior. We get kind of this jagged behavior. If no yield strength is apparent or we don't have this peak, we actually use a 2% offset to determine where that plasticity has begun. After a period of time, enough stress, all those dislocations basically have been taken out of play. They've either reached a grain boundary, a precipitator, or a second phase, or they can no longer be pinned by solute atoms. So what happens is we need increasing stress to yield that material, and what it does is we actually start creating new dislocations, and we start slip on different crystal axes, those stronger axes. We actually get uniform cross-section reduction during this. Ultimately, we will get to a point known as the ultimate tensile strength, where this buildup of dislocations, vacancies, they coalesce, they lead to microscopic cracking. So you end up with a reduction of cross-section area. You get localized plastic deformation and necking. Ultimately, these micro cracks coalesce into larger cracks. This accelerates the necking and ultimately leads to failure. So those are the strengthening mechanisms. Again, from a practical standpoint, what does that mean? If we go back and look at a low-carbon steel, we have a ferrite-pearlite structure. Here the ferrite governs. So we have a lower yield strength, but very ductile. As we increase the carbon level, and that's lower carbon is curve 1. As we increase the carbon level, we start getting more and more contributions, by the pearlite. So we end up with a stronger steel. We do have some moderate influence from the pearlite last spacings. As we go to very high carbon levels, we have no interaction from the ferrite. It's still there between the cementite lasts. We have all our structure based upon this very strong cementite. As a result, we get very poor ductility. So if you consider the yield strength 1 of a low carbon steel, and as a designer I want a higher strength steel so I can have a lighter shape, I can trade that off by going to a higher carbon, say, to get the yield strength 3 versus yield strength 1. But here's what I do. I trade off elongation. So you can see a dramatic reduction. The thing is with steelmaking is we cannot improve one property without influencing other properties. So the long answer is how does the mill control the properties of the steel? Well, we have varying degrees on the control of the process variables. again, we cannot make an improvement in one property without influencing other properties. Diagrams up here show you basically in a cartoon scale the relative influences. I can increase grain strength, get a finer grain size, but I'm going to reduce yield to tensile ratio. I can increase carbon level, but I get to a point where my yield strength peaks and drops off, but my trade-off is elongation. So as a steelmaker, we seek to optimize the total package of properties in a cost-effective manner to meet the grade requirements. Last question. If I retest the product, will I get the same results as in the mill test report? Well, very simple answer. The exact same values? No. Nominal values? Yes. Well, why is that? Let's look at what we'll get from a chemical standpoint. The casting method is going to strongly influence the variability in a product check. There's really two routes to get to structural products. The historic route is ingot cast. The current route is continuously cast. If we compare those two, in the ingots we have a range of killing. We have killed, semi-killed, capped, and rimmed. Whereas in continuous casting, this must be fully killed. And I'll talk about killing here in a moment. Solidification rate in an ingot is very slow, whereas in continuous casting it can be very fast. As a result, in ingots we can have considerable segregation, whereas we have very minimal in continuous casting. Also, ingots, they're a single heat, whereas continuous cast can be a sequence heat. All of this will give us variability in the chemistry. Question often comes up, what is a killed steel? What do we really mean by that? Well, let's look at the soda analogy. If we take my favorite green caffeine soda, as delivered by the manufacturer, it has carbon dioxide dissolved in the liquid. It's not really apparent. You get a few bubbles every now and then. But if I was to shake this up and relieve the top, this dissolved carbon dioxide comes out of solution as gas bubbles. It escapes, and I have a volume reduction. That volume reduction is due to the loss of that carbon dioxide in solution. Same thing in steel. In the liquid state, steel has dissolved gases, hydrogen, oxygen, and nitrogen. As I cool them down, as I go to a solid, they actually lose the solubility. They come out of solution. If sufficient oxygen is dissolved in the steel, it can react with carbon, forming a carbon monoxide bubble within the liquid steel. What happens is I get a local reduction in the carbon content, and I may get a trapped void within the steel. Here's actually a continuous cast section where there's been gross gas evolution. It graphically illustrates what happens when gas comes out of solution. So as the solidification front moved forwards, the gas came out of solution, got trapped in the casting. In ingot steels, semi-killed, capped, and rimmed, they actually encourage that to increase the volume and get away from the shrinkage port. So in a killed steel, what I actually do is I add elements such as aluminum or silicon that reacts with this dissolved oxygen, so it takes it out of play, like the carbon dioxide coming out of the soda pop. It's removed. It can no longer form a bubble. So I get a completely solid shape versus something that's filled with bubbles. We also talked about segregation. Segregation is a time-temperature process. When a solidification front moves forwards, the higher melting point constituents will want to solidify first. They will actually reject lower melting point things. So what happens as a solidification front moves through a liquid, it becomes enriched in the lower melting point constituents. As a result, we get regions of fluctuating compositional constituency. If we take our traffic example again, here's an example where traffic came to a very fast halt. And if we consider the motorcycle riders, in this case, say they're sulfur atoms, they're very well dispersed through the matrix. So we have very low segregation, very chemically homogeneous, versus a situation where the traffic has come to a very slow halt. Very similar to slow cooling. What has happened is the motorcyclists or the sulfur atoms have been able to be pushed out from amongst the cars, and they are highly segregated. Comparing the two graphically illustrates where segregation can go. So you can get variability in the chemistry due to Slower cooling, again, that tends to be predominant in ingots. From a continuous cast standpoint, we do something called sequence casting. In continuous casting, we have a ladle of steel. It's transferred to a tun dish, which then gets transferred to a mold where it solidifies. When this ladle runs out of, say, heat 1, we'll bring in a second ladle of chemistry 2. We will team that into the tun dish. So for a period of time, we are actually going to have a tun dish that has a mixed chemistry. Given time, it's going to decrease in the heat 1 chemistry, and it'll increase in heat 2 chemistry. To a certain point, it'll be 100% heat 2 chemistry. When this ladle is finished with heat 2, we will repeat the process with heat 3. So if you go do a product check on a piece of steel that you have received that's been continuously cast, you will find that heat 2 will possess a changing mix on one end of the bars or the lot that has a mix from Chem 1 to Chem 2 on one end, Chem 2 in the center, and then a variation from Chem 2 to Chem 3 on the other. So it all comes down to where you sample that. So there will be a variation across the heat and chemistry. ASTM A6 defines what that can be, and it's up to the steelmaker to make sure he operates within those requirements and limitations of A6. Essentially what you're going to see in the mill test report is, as a steelmaker, we're going to be sampling this throughout the casting process, and you're going to get an average of that chemistry. So yes, there will be variation in chemical results if you do a product check on your mill test report. What about physical properties? Well, there's a very little referred to but very important appendix in ASTM A6 that deals with the variation of tensile properties in plates and shapes. It says that the tension test requirements are intended only to characterize the properties. They're not to define the properties at all possible locations. It's well known and documented that there will be variations within a heat or an individual piece, and the engineer or designers to use sound engineering judgment. There is an expected variability. They define what that expected variability is, and that's based upon historical experience. Maybe a little worrying to some engineers, but what ASTM does report in its annex is that these test procedures have been found to provide a structural product that is adequate for normal structural design criteria. So yes, you will find some variability. There can be some additional variability based upon how that shape, plate, etc. is actually sampled. Let's use the example of thick W shapes. You may be aware of the core area. ASTM defines that as 1.5 inches. AISC in the spec manual defines that as 2 inches or greater. Essentially, the core area, this box here, is an area where you have the highest thermal mass, so you're going to have the highest grain growth occurring. It's also in the center of the shape, so you're going to have the lowest reduction ratio, so you're going to have a coarser grain size plus this grain growth due to the thermal mass. It's also an area in ingot casting that you may see dramatic sulfur and phosphorus segregation, so you're going to have reduction in tensile strength and elongation. So correct location for Sharpies. Well, that's a graphic illustration as to some of the variabilities we see across the shape. As an engineer, should you be concerned? Well, the coupon types we use in the mill are called out in ASTM. They are given a specific location to be taken from. They're full thickness, 8-inch gauge, and they are given as a plate straps type sample. That's defined in ASTM A370. The problem comes in, these can be very large, particularly for very large shapes. Independent testing labs, third-party testers may not have the equipment of sufficient capacity to actually test one of these shapes. So what they tend to do is go to a smaller coupon, a 1/2-inch round coupon. It has a different gauge. Okay? The problem comes is due to this variability across the thickness of the shape, we can end up with different results with those 505 rounds. The 505 rounds basically are giving localized properties. They do not give the same values as plate specimens. They will show microstructural and chemical differences, and they can be the differences can be exaggerated as the thickness increases, or you have a particular processing such as the quench self-temper in A913. For instance, the plate specimen is going to give us an average behavior across the entire thickness. Think of it as testing the entire thickness of a piece of plywood, whereas the 505 you may be testing individual laminations in that plywood. So if the red line is what I'm reporting on the mill test report from the full thickness specimen, I can get, based upon locations, 1, 2, or 3 as shown here in the shapes, I may get different yield strengths that are greatly exaggerated by location. Again, due to chemical differences, due to grain size thicknesses differences. So the question, will I get different results on the MTR if I test it? Again, the long answer is similar to the short answer. Exactly the same values? No. Nominally the same values? Yes, within the allowable variations, given that the mechanical properties are determined using the same coupon locations. Okay, I know it's a lot to absorb. Probably gone through it very quickly. I've seen a lot of questions flash up here. We basically addressed what's the difference between iron and steels, why are there multiple grades, how does the mill control chemistry, and if I test a product, will I get the same results as a mill test report? That was our goal. Thank you very much. If you have any further questions, please feel free to contact the AISC Steel Solutions Center. And Brent, I'm going to pass it back over to you.
Okay, thank you very much, Doug. I do want to go over again the CEU and PDH process, but before we do that, we do have a couple minutes. I would like to just address a couple of questions, Doug, if we could.
Yes.
One question is there a source that compares all the various classifications or designations that come from various grading organizations?
No, there's not. There is some literature out there that will address some of the organizations. That's a question I'm asked very often. Again, some of the basis for this talk. The ASM, American Society for Materials, has a Metals Handbook desk edition that does mention, if I recall, some of these differences, who they are, but really it's individual research into what the specs are to find out what the differences are, or talking to somebody who uses them on a daily basis. Even there, as I put in the one slide, the little fellow sitting there with stars going around his head. Even if I train my metallurgists and salespeople here at SDI, there is still confusion as to the different grades and their applicability. So I don't know that there's a simple, concrete answer to that.
Okay. We had a couple of questions. I'm going to lump these together. I'm not sure they necessarily go together, but they involve chemistry. Can we add any chemicals or other metals to stop microcracking? Another question is, has the issue of laminar tearing been solved by improved steel chemistry?
The laminar tearing, I'm going to address that. Steelmaking techniques can play a lot into that. The level of inclusions, the type of inclusions you have, where they show up in the shape. A lot of laminar tearing comes into, in my experience, weld joints. There may obviously be some other applications there. Cleaner steel practices will give you better behavior there. Although I did say from a yielding standpoint, material is isotropic. From a laminar tearing standpoint, steel is anisotropic. Really, the roll reduction elongates the grains. The analogy to hot-rolled steel is that of wood. You will have long grains. You do have different properties in wood depending upon the orientation. You can cleave very easily in one orientation. In wood, you have to saw to go perpendicular to that. Microcracking, probably along the same lines as we're talking here, laminar tearing. That's a very broad subject. I don't know that I could address that in just some very higher level discussions.
Okay. Another question, can the grain size affect the oxidation process?
I don't know how to answer that question. I'll have to make an assumption of what the question is asking. Oxidation processes is basically taking place in the liquid, or deoxidation is taking place in the liquid. Grain size is in the solid. So they are opposite. Level of deoxidation will not affect grain size. The grain size, again, comes down to roll reduction, microalloying, and other factors like that. They're kind of separate, distinct parts of the process.
Okay. And then someone asked about the expression equivalent carbon content. Can you discuss on this and its importance?
Yeah, I'm going to go back to a slide here real quickly, slide 77. If we look at this little graph here, increase in strength versus weight percent in element, there's two ways to look at carbon equivalent. Most often it is used in welding. It can also be used in heat treatment. It can also be used in building or designing strengths. If you look, and again, this is a very rough cartoonish type graph just to give you a feeling of how these things interact. If you take all these various elements and their influences on strength or weldability and consider them just to be carbon and what that effect would be, that is your carbon equivalent. It's basically a mathematical modeling to predict. It is very difficult in an alloy if I have more than two phases to predict the behavior. So if I can simplify that down to just pure iron and carbon alloy, I can more easily predict its behavior. So that's what carbon equivalently attempts to do. Don't know if that's a sufficient answer for the person asking.
No, thank you very much, Doug. And then one other question I see here is, do you have any suggestions for further study on this topic of metallurgy?
It depends how deep you want to go. There was a book out there. Now there's going to be a run on eBay because it's out of print. Linnert, Welding Metallurgy is one of my favorites to refer to. He goes into it maybe a little bit deeper than I have. Instead of the 20,000-foot view, maybe he brings you down to the 3,000 or 4,000-foot view. The first half of that book basically goes over a lot of the concepts that I've used here. I relied upon him very heavily to check my facts and figures. ASM, American Society, again, for Materials, has a series of courses out there, Metallurgy for the non-metallurgist. You can take it in a classroom setting. You can take it as a correspondence setting. They have a corresponding textbook that goes with that goes much more in depth into the metallurgy, the grain sizes, the grain types, strengthening. A lot of what we talked about also goes into the non-ferrous. They do have sections there on the ferrous. They go into the various types, not only just the structural, but they may go into bearing steels and stuff like that. You can check online. If you check things like Wikipedia and look up steel or any of the topics that I've talked about, you can find some links there. I'll be careful with that because, you know, the old expression is if you have 5 metallurgists in the room, you're likely to have 6 or 7 opinions. Some people do post things there that are, of course, the web is wide open. But the published references are a good start. If you want to go a lot deeper, there are a number of textbooks out there. I could recommend those too if someone wants to send you guys an email, and I can put together a reference list if you'd so like.
Okay. Thank you very much, Doug. And I did want to correct you on one item you brought up earlier, and that was your audience today. I did have someone let us know there was one other metallurgist in the audience. So just want to let you know what else we have going on at AISC as far as continuing education. Our fall schedule has taken off. We're in 22 different cities 4 different seminar topics, including the new 14th edition manual seminar. Check us out on our line at aisc.org/seminars to find a city near you. And I just would mention also that that 14th edition seminar is just starting this fall, and it'll continue for several seasons. So if it's not coming to your city this fall, look for it in the spring or fall of next year and beyond. We also have a steel camp this fall. If you haven't heard about this, this is a 2-day continuing education event we've put together. The one happening this fall is in Charlotte, North Carolina, October 6th and 7th. If you're in that area, I highly encourage you to make time for it. Speakers such as Dwayne Miller, Jim Fisher, Bill Thornton, Mike West will all be presenting. We've put together an excellent 2-day event there. And I appreciate everyone that was here today. We hope you'll join us for another webinar. We've got a couple on the schedule for this fall. We may be adding more, but we typically run these about once a month, and we've got 2 on the schedule right now. In October will be Dr. Joseph Ura on stability, and in December we'll be talking about the new composite design provisions. And if you are looking to schedule continuing education on your own time, you can always go to e-learning. We've got over 80 hours of recorded presentations that are available at any time, and those are always free to view. And if you're looking for PDHs, it's a nominal fee to purchase, take, and pass a quiz so that you can get your CEUs on that. Lastly, I ask everyone if you just take a moment, when we conclude today's presentation, a survey is going to pop up, just a few questions. If you could give us your feedback, we'd greatly appreciate it. I want to give a special thanks again to Doug Reese-Evans of Steel Dynamics for his outstanding presentation. Thank you all for participating in Steel Day in today's webinar. There's a lot of daylight left out there. I encourage you to stop by one of the local Steel Day events out there and continue to get a better understanding and learning of what's going on in the steel industry out there. Happy Steel Day, everyone, and have a great afternoon.